now we're going to summarize videos 128A, B, C, D, where we use the shell method to calculate volumes for solids of rotation. And we just discussed the washer method, the disk method previously. And what we found there was whenever we had an axis of rotation, our differential, which involved our integration, it was always going to be parallel to your axis of rotation. In the shell method, you'll see the opposite occurring. For all of our axis of rotation, we're going to integrate in a direction that's perpendicular, so the differential is perpendicular to the axis of rotation. In the first one, video number 128A, we rotated about the vertical line x equals 0, which of course is the y-axis, the area between two curves, y upper minus y lower, with y lower being equal to 0 in that particular video, and we were asked to use the shell method. So the method involves a sketch of the vertical axis, x equals 0, the axis of rotation, and we draw the cylindrical shell around this axis, and the radius is r equals x distance, and the integral being perpendicular to the axis of rotation, we're integrating horizontally, so we're integrating over x, and the differential is dx. For video 128b, we were asked to rotate about the line, the axis x equals 0 again, so that again was the vertical axis, the area between two curves, y upper minus y lower, with neither of the curves being the x-axis. That's what made this example different, using the shell method. So the sketch is very similar. And again, the differential is dx. We're integrating over x as we nest these shells outward from the center outward. And then video 128c, rotate about the y equals 0 axis of rotation. Okay, now that's the x-axis. That is a horizontal axis of rotation. We're going to rotate the area between the curves y rightmost y value minus y leftmost y. It's actually a function. It's a function. Y is a function of x. Rightmost minus y is a function of x leftmost, with neither curves being the y-axis, and we're going to use the shell method. So now we draw our horizontal axis of rotation, y equals 0, and you see now our radius for our shell, our sample shell there, you see that that radius is r equals y instead of x, and we are going to nest outward from the center, from the axis of rotation, which means now we're integrating over y. We're integrating in a vertical manner, and our differential is dy. And our last example for the shell method, 128d, we saw that video where we were asked to rotate about the line x equals 2. X equals 2 is back to a vertical axis. It's a little different than the first two examples because it's not x equals 0. It's not the y-axis. It's off the y-axis. Nevertheless, it is a vertical axis of rotation. We're going to rotate the area, or we did rotate the area between the curves y upper minus y lower, where y's were functions of x, with neither curve being the axis of rotation. So it was a different value that was the axis of rotation. And as that's what makes it different than video 128A and 128B. So we're using the shell method. We have our vertical axis of rotation, x equals 2. We draw our sample shell around the axis of rotation. And because if you did a sketch, you could see that the radius no longer is just x like it was in the first two videos. In this situation, we have to take the entire distance 2 and then subtract the x value to get the distance that we're going to, the radius for our shell. And of course, because we have a vertical axis of rotation, we're integrating in a horizontal manner over x, and the differential is dx.